Okay guys, welcome back and good morning. Continuing with our review of electrostatics, I wanted to walk you guys through one of my favorite expansions, and that's something called the multipole expansion. Now that's multipole, not multipole. There's a shun, once again, implied. Now to do this, we're going to imagine we have this nice charge distribution, and we're going to place our origin of coordinates somewhere within it. We're going to talk about what is the potential out at some point P not in the distribution. In fact, later we're going to insist that that point P is in fact very far away from this distribution, but we'll get to that. So as before, the distance out to our field point is little r, and we want to draw a nice primed vector out to some little volume element. There it is, that occupies some amount of charge that's in this density. And to get from there out to the field point P is that familiar script r. We'll also need, for reference, this angle formed between the vectors. We're going to call it beta. So to solve, we're going to want to use the law of cosines to find this script r in terms of these other two r's. So keep this picture in your mind, because it is going to disappear. So we have that triangle. Now let's motivate first, why are we doing this? Well, as we could probably remember, we talked about this electric potential last time. We can write it in terms of a charge density very simply, that we have the familiar constants, and then we have rho divided by that script r integrated over the volume. So what we're going to want to do is ultimately perform an expansion based on this script r. First, let's write it down. Law of cosines tells us, and we're dealing with magnitudes here, that one side of a triangle is equal to the other side squared plus the remaining side squared minus 2r prime, since both of the remaining sides, times the cosine of the angle between them. This one's actually squared as well, and that's why we needed to define that beta from before. So the first thing we can do is simply pull out an r squared from all of these. So you say r, script r squared is equal to this little r squared times 1 plus r prime over r, quantity squared, minus 2 times r prime over 1r times the cosine. So with this in mind, we can suggest a small quantity with which to perform this expansion. So what we're going to say is we're going to take this little epsilon and define it to be r prime over r times r prime over r minus 2 cosine beta. This is where the approximation is going to be important. We want to say that we're very far from the field point, that r is much greater than r prime. So we're very far away from the charge compared to the size of the charge distribution from the origin. – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – This would directly imply that this epsilon is small compared to 1, because you can see the little r is in the denominator as compared to the r prime. So with that, we can actually rewrite our script r in terms of this epsilon. It's going to be equal to 1r this time, since we've taken a square root, times the square root of 1 plus epsilon. Then the potential, we have 1 over script r, so let's write that down. 1 over script r, 1 over regular r, times 1 plus epsilon to the minus 1/2. That's just the same thing as 1 over a square root. And if we're going to be expanding in terms of small epsilons, and we're talking, of course, about a nice old Taylor expansion, this is what we would get. 1 over script r. We leave this r out here because it's not really what we're saying is small. But if we're expanding this square root, we get 1 minus 1/2 epsilon plus 3/8 epsilon squared minus 5/16 epsilon cubed, and so on. It'll alternate sign like that, and we'll get various coefficients in increasing powers of epsilon. And that's, in fact, a very interesting formula that you may recognize. This actually lends itself to suggestion that, in fact, the Legendre polynomials are involved. These polynomials that you may or may not be familiar with follow this exact pattern. Now, how can we introduce these Legendre polynomials into our definition? Now, the Legendre polynomials, named p sub n of whatever argument you choose. Here we're choosing cosine beta as the argument, and n is just some index to tell you which polynomial you're on in an infinite series. 1 over script r can now be written in terms of the regular r as a sum over n, so r prime over r to the nth power times the nth polynomial. Now that's just lovely. We can introduce this into our equation for the potential. So the potential now at a point r is equals to the familiar constants, sum over n. As you see, we have 1 power of r here. We'll get n powers of r there. So we'll have 1 over r to the n plus 1. Then an integral over r prime to the n. It's just right there. The nth Legendre polynomial. I'll omit the argument. I think we know what it is. And the charge density rho, integrated over the volume, d3r. And it's, of course, the prime coordinates, which is also what rho is a function of. So this is effectively the multipole expansion. Is expanding in higher orders of n. So we can break down a few terms. Let's consider just what the first 3 terms would give us. The first term, if we truncate at n equals 0, is called the monopole term. And V monopole is pretty easy to write down. 1 over 4 pi epsilon 0 times the total charge Q over R. And that's exactly it. Now this is exactly right if you just had a point charge, a value Q. This would be the potential at all points in space. But of particular interest to us is, what if there is no net charge? What if the overall charge of the system is 0? Well, that would mean that this term vanishes. Normally this term dominates in the expansion. The leading terms are the largest. But if their contribution, in this case the electric monopole, is non-existent, we have to move on. If you look at the next order of the expansion, n equals 1, that leads us to a dipole. And here you can see why it's called multipole. We're talking about the various poles that can exist. The dipole equation, V dip, is a little more complicated. We have the familiar constants, and this time it's going to be over R squared. Since of course there was an n dependence, it was R to the n plus 1. So we get the squared. We're going to dot in the unit vector R to an integral, which will be important, R prime cosine of beta rho of R. Of course, integrated over the volume. But this quantity here is significant to us. This quantity, which is a vector, we're going to call little p, which is the dipole moment of the charge configuration. So we can effectively rewrite the dipole potential in terms of this dipole moment. It's just equal to P dot R divided by 4 pi epsilon 0 R squared. So if you know the dipole moment, you can immediately write down the potential. This dipole moment will be useful. A dipole moment is when you have an imbalance in charge, a greater positive charge on one side, greater negative charge on the other. But you can imagine many situations where there's in fact no dipole moment either. So we introduce the next term, n equals 2, called the quadrupole moment. We'll define this quadrupole moment up front. It's a second rank tensor now, indexed by I and j for different points in space. The monopole moment was a scalar number. Dipole moment was a vector. Now we've moved on to tensors. We define it as 1/2 an integral 3 Ri times Rj minus R prime squared Kronecker delta Ij multiplied by the charge density integrated over the volume. So a little bit of a more complicated definition, but this gives you quadrupole moment at all points in space. And just in terms of this quadrupole moment, we won't even write it down in terms of a rho this time, since the rho is in fact within this term. We'll write it in terms of the usual constants. Now a cubic dependence on distance, a sum for I and j of the quadrupole moment multiplied by the two unit vectors. And this term falls off very quickly as r, now r to the cube. Now this increases by doubling every time to octupole and so on. But this is the highest order pole I've ever seen people actually deal with. Now of course we'll be applying these different pole and this multipole expansion in general to materials, to atoms and molecules in the coming videos. But that's it for now.